Okay, so we're going to talk about these things called indeterminate forms and L'Hopital's rule. I know it looks like Le Hospitals, but he was a French guy, so L'Hopital. And this is actually going to bring us back to limits, so something we did at the very beginning of the year. But L'Hopital's rule involves taking derivatives, so we didn't have the means to do this until now when we developed all our rules for taking derivatives. All right, so just to get us started, you don't have to write this down. This is just to give you some intuition for what's going to be happening. Let's say we're trying to analyze the behavior of this function. And in particular, we want to know what goes on with that function as we get close to 1. So really, we want to know the value of the limit as x approaches 1. Well, remember the first thing we generally try to do when we evaluate limits is just a direct substitution. But if we tried to do a direct substitution in this case, we would end up with natural log of 1 over 1 minus 1, which is 0 over 0. Now, we had already talked about this in the past. This is not undefined. This is what we call an indeterminate form, which means it may exist or it may not exist. We just can't currently tell in the form that we have. So what we did in the past for this was generally we tried to manipulate it algebraically. Can we simplify this algebraically and get it into a form where when we make the substitution, it doesn't end up being 0 over 0? But in this case, there's nothing you can do to simplify this algebraically. All right. And this is just explaining something that we've already talked about, that 0 over 0 is an indeterminate form, so the limit may or may not exist.
Can you go back for a second to the first slide?
Yeah.
Thank you.
So this is all just kind of review. In the past, when we had something like this, where we had an indeterminate form, right? If I were to plug 1 into x here, I would end up with 0 over 0. But there I can factor, I can divide out the x minus 1, then I can make my direct substitution of 1 in for x, and I end up with 1/2. All right, we can't do that with an indeterminate form with a function like this, because there's no way to simplify it algebraically. This slide, we're just talking about the same idea here. If I let x approach infinity instead of 1, well, natural log just gets indefinitely large. The denominator would be infinity minus 1, which is indefinitely large. So I have basically a situation with infinity over infinity, which is another kind of indeterminate form. The limit may exist, the limit may not exist. We don't know. So L'Hopital's rule is something that allows us to evaluate indeterminate forms. And here, I'm going to give it to you. This is L'Hopital's rule. The real important part is if you have an indeterminate form of either of these types, then L'Hopital's rule says that the limit as x approaches a of f of x over g of x is the same as, is equal to, the limit as x approaches a of f prime over g prime. So basically what L'Hopital's rule tells us that we can do is if we're trying to evaluate a limit and it comes out to an indeterminate form, we can take the derivative of the numerator, take the derivative of the denominator, and then try to reevaluate the limit. And whatever that limit comes out to is equivalent to the original limit. Okay. So let's just jump to the first example that we looked at. The first thing you need to try for any limit is direct substitution. So as we saw, if I just plug in 1, I have natural log 1 over 1 minus 1. Natural log 1 is 0. 1 minus 1 is 0. This is an indeterminate form. All right. So since it's an indeterminate form, I'm allowed to apply L'Hopital's rule. Here's the general notation you'll see when we apply L'Hopital's rule is you'll see the equal sign with the H just to indicate that that's what we're doing, and that just stands for, hey, I'm applying L'Hopital's rule here. So this is equal to the limit as x approaches 1 of the derivative of the numerator over the derivative of the denominator. So help me out in the chat. And we're not using, this is not the quotient rule. This is just the derivative of the numerator over the derivative of the denominator. So what's the derivative of natural log x? One over x. Yeah, Audrey, sorry. This just means that it's just the notation we use to show, hey, I'm applying L'Hopital's rule. If you guys didn't catch that. So the derivative of the numerator is just 1 over x over, what would the derivative of the denominator be? What's the derivative of x minus 1? So just 1. Perfect. So now I can just simplify that. That's just 1 over x. Plug in the 1. There's our limit. Right, so in the past, if I asked you guys to evaluate something like this, your only recourse, because you can't simplify it algebraically, your only recourse would have been to go to your calculator. And I'll just kind of remind you what that would have looked like. It takes my calculator a while to open. Here we go. So we could have evaluated it kind of numerically by going, okay, let's plug, oh. So I would have gone natural log x divided by x minus 1. And then I could have just gotten real close to 1, right? Like 0.9, 0.99, 0.999. You can see it looks like my y values are just getting closer and closer to 1. And from the other side, that's the same. But at 1, we're not defined, right? So there's a hole in the graph at 1, but you can see that the behavior is it's the same on both sides of 1. But now we have a way to sort of do this analytically using calculus, and that's just L'Hopital's rule. So let's just take the derivative of the numerator, take the derivative of the denominator, and try and reevaluate the limit. The important thing to remember is you first need to verify that it is in an indeterminate form before you try and apply L'Hopital's rule. All right, let's see another couple examples. So 0 over 0 and plus or minus infinity over infinity are not the only ways an indeterminate form can arise. And so we can have these things called indeterminate products. Oh boy, this slide is messed up. I apologize. So an indeterminate product, just ignore all this, will arise when you get the form 0 times infinity. You might think, well, shouldn't that be 0? But remember, infinity is not a number, it's a continued process. So no, 0 times a constant is 0. Infinity is not a constant. So this is an indeterminate, another type of indeterminate form. And this type of indeterminate form can be rewritten just to be in one of the original types of indeterminate forms. And the way we rewrite it is we rewrite the product like this. So a product f times g is equivalent to f over 1 over g, or g over 1 over f. And so by rewriting your product as that kind of a quotient, it'll put it in one of these two types of indeterminate forms. And those are the types that we can apply L'Hopital's rule to, okay? So really the idea is, if you had 0 times infinity, you should be able to rewrite that as 0 over 1 over infinity. And remember that this, if you have a constant over something getting indefinitely large, this fraction will approach 0. So really now I have an indeterminate form of the type 0 over 0. And that I can apply L'Hopital's rule to. So let me show you what I'm talking about with an example. Let's say we have the limit as x approaches 0 from the right of x times natural log x. If I do a direct substitution of 0 in for x, I just have 0. Now natural log x, what I want to show you is, let's look at the graph of natural log x. All right, that's that graph here. So as I approach 0 from the right, you can see that my y values get negative quickly because 0 is a vertical asymptote of natural log x. So my y values are approaching negative infinity. So what I have is 0 times negative infinity. All right, that's an indeterminate product. So we need to rewrite this product as a quotient. And you can choose to do one of two things, right? I could write it as x over 1 over natural log x, or I could write it as natural log x over 1 over x. Keeping in mind that we're going to be applying L'Hopital's rule, so we're going to have to take the derivative of the numerator and the denominator separately. So that kind of helps you make the decision about which way you're going to write your quotient, because both of them will come out to indeterminate forms, but one way is going to be easier to apply L'Hopital's rule to than the other. So this way I would take the derivative of natural log x and the derivative of 1 over x separately. The other way I would take the derivative of x, and then I would have to take the derivative of 1 over natural log x. The problem with this is it's going to be kind of difficult to take the derivative of 1 over natural log x. You're going to have to use like chain rule, and it's going to be a bit messier. So I'm going to opt to write my product or my quotient the other way. I'm going to write it as natural log x over 1 over x. And so let's just verify that this is an indeterminate form. Well, we already know that as x approaches 0 from the right, natural log of x approaches negative infinity. What about 1 over x? Well, we can just look at this as a graph. So here's 1 over x. As we approach 0 from the right for 1 over x, so we're going this way, right? My y values get infinitely large, so positive infinity. And any combination of infinity over infinity, positive or negative, is an indeterminate form. So I have an indeterminate form that I can apply L'Hopital's rule to now. All right, so I'm just going to give it the equals with the h over it to indicate that that's what I'm doing. So, derivative of the numerator, derivative of natural log x is just 1 over x. What is the derivative of 1 over x? Well, remember that 1 over x is the same as x to the negative 1, right? So we can just use the power rule. Close, Dylan. So it's not negative 1 over x, but it is negative x to what power? Good. Thanks, Naomi. So negative 2. So that's actually negative 1 over x squared, right? All right, so the derivative of the denominator is negative 1 over x squared. Before you try and evaluate the limit again, simplify, okay? So I can simplify this by flipping the bottom fraction and multiplying, right? So that's 1 over x times negative x squared over 1. And then this can reduce. I can divide out one of these x's. And as x approaches 0 from the right of just negative x, now I can do just a direct substitution, plug in 0, and I get 0. There's a couple more ways we can see an indeterminate form arise. So there is a thing called an indeterminate difference, and that takes the shape of infinity minus infinity.
There's more.
Go back.
Can you go back, please? Yeah.
So indeterminate differences, because, right, infinity isn't a constant, it's a process. This isn't necessarily just 0. It could be 0, or it could be the case that the first infinity is getting large much faster than the second, so the overall difference is still going towards infinity. Or it could be the case that the second infinity is getting large much faster than the first, and it's going towards negative infinity. Or they could even each other out, and they could, the difference could be a constant other than 0. So again, what we want to do is somehow rewrite this so that it takes the form of an indeterminate of 0 over 0 or infinity over infinity, so that then we can apply L'Hopital's rule to it. So let's see here. We're going to take the limit as x approaches pi over 2 from the left of secant minus tangent. All right, well, secant is 1 over cosine, right? And tangent is sine over cosine. And so if I'm looking at the limit as x approaches pi over 2 from the left, the one thing I want to point out is that cosine of pi over 2 is 0, right? So if we look at our unit circle, pi over 2 is here at the top. It's a 90-degree angle. The coordinate there is 0, 1. Remember that cosine is the x-coordinate. So cosine of pi over 2 is 0. So as I approach pi over 2, cosine is getting closer to 0. So whenever I take 1 over something that's getting closer to 0, the whole fraction is going to get closer to infinity. And the other way we could deal with that is to just graph it and verify graphically what's going on as we get close to pi over 2, right? So if I look at just y equals secant and then we may not be particularly familiar with where pi over 2 is, so I'll just graph it as a vertical line. So x equals pi over 2. So it's that green line right there. So as we approach pi over 2 from the left of that green line, I'm looking at this blue branch of my secant graph. Secant is approaching positive infinity, right? Okay. So I have infinity for secant minus, what about tangent? Tangent has vertical asymptotes as well. There's tangent. Pi over 2 is still the green line. As I approach it from the left, I'm along this branch of tangent, so you can see the y values are approaching positive infinity as well. Great. So I do have an indeterminate form of type infinity minus infinity. All right, with trig, the best thing you can do when you have an indeterminate form of this type, because you want to rewrite it as a fraction, that's our whole goal, is just get everything in terms of sine and cosine, which I've already done here, right? Secant is 1 over cosine, tangent is sine over cosine, and then combine the fractions. So they already have a common denominator, so this one's kind of tailor-made for me to rewrite. So x approaches pi over 2 from the left. Now I have 1 minus sine over cosine. All right, well, if we did a direct substitution of pi over 2 here, I've already drawn a little unit circle off to the left there. We know that cosine of pi over 2 is 0. What's sine of pi over 2? Yeah, it's 1, so I would have 1 minus 1. Boom. I have an indeterminate form of type 0 over 0, and that I can apply L'Hopital's rule to. We'll just do equals my h. All right. What is the derivative of my numerator going to come out to? The derivative of my numerator. So just the derivative of this. Good. Negative cosine x. So derivative of 1 is just 0. Derivative of negative sine will be negative cosine. What's the derivative of the denominator? Negative sine. All right, now let's do a direct substitution. We know that cosine of pi over 2 is 0. We know that sine of pi over 2 is 1. So I get 0 over negative 1. 0 divided by negative 1 is 0. So that's my answer. I want to mention the other option you have, if it's not trig that you're dealing with and you end up with an indeterminate form of infinity minus infinity. One way you can always make something into a fraction is by multiplying it by its conjugate. So let's say I have just a minus b. I can always multiply by a plus b over a plus b. Then your numerator is going to simplify to a squared minus b squared over a plus b. And that'll generally get you to the place where you have an indeterminate form of infinity over infinity or 0 over 0. And you can then apply L'Hopital's rule. Let's see, I think we have one more type. Yeah, we have one more example to get to. That's indeterminate powers. So there are a couple types of indeterminate powers, but the approach is basically the same. So you don't have to write all this down, but I would write down the far right column. The three types of indeterminate powers are 0 to the 0, infinity to the 0, or 1 to the infinity. So this is the case where you're taking a limit as x approaches a of f of x to the g of x power. I don't want to rush you, so give me a hand raise again when you're good on this slide. All right. So basically, here's the process we're going to use. We're going to get it written as an indeterminate product first, which remember was a product of the form 0 times infinity. And we're going to do that by taking natural log of both sides. And there's that property, remember, of logarithms that if you have natural log of a to the b power, you can bring b around to the front as a coefficient, so that becomes b times natural log a. So that's basically what we're going to do here. Once we have it as an indeterminate product, we know how to rewrite it as an indeterminate quotient. Once it's an indeterminate quotient, we can apply L'Hopital's rule and evaluate it. But there's going to be one more step at the very end, because we're going to have natural log y on the left-hand side, and what we're trying to look for is not natural log y, but just y itself. So at the very end, we're going to be exponentiating both sides by e to get rid of the natural log. So it's probably best just to do this as an example. You don't have to try and write this slide down. You can follow this example. All right. So let's look at what we have here. We got 1 plus sine 4x to the cotangent x power. And we're approaching 0 from the right. If I look at my unit circle, that's 0 there. And that point is 1, 0. Remember that the y-coordinate is sine. So if I do a direct substitution, I get 1 plus 0 here. Now cotangent, as we approach 0 from the right, let's do that one graphically. All right, so there's my cotangent graph. I'm looking at what's going on as I approach 0, so that red vertical line from the right. So we're on this branch of cotangent. You can see that my y values just get infinitely large, right? So cotangent's going to infinity. All right, so I have an indeterminate power of type 1 to the infinity. All right, so here's what we want to do. We're going to set this whole thing equal to y. So y equals the limit as x approached 0 from the right of 1 plus sine 4x to the cotangent x power. And sorry, I actually just want to set y equal to, I don't need the limit there for now. I just want to set y equal to this. And then what we'll remember is at the very end, we want to take the limit as x approaches 0 from the right of y, since y equals that. Okay. But before we can do that, we want to get it to be an indeterminate form that we can apply L'Hopital's rule to. So we're going to introduce our natural log here. Let's take natural log of both sides. So ln y equals ln of the right-hand side. All right. So now we're allowed to bring the cotangent, that power, around as a coefficient. So what we have is natural log y equals cotangent x times natural log of 1 plus sine 4x. All right, so now I want to be clear. If we look at my limit, if I take the limit as x goes to 0 at this point, cotangent is still going to infinity. Sine of 0 is still 0, so I would have natural log of 1, which is 0. So now I have that indeterminate product that I want of type infinity times 0. And I'm just going to rewrite this as a quotient. So to rewrite it as a quotient, you have to divide by 1 over one of the factors. And you can choose which one you want to divide by the reciprocal of. So I could either divide by the reciprocal of cotangent or the reciprocal of natural log. I think cotangent is going to be easier. What is the reciprocal of cotangent?
Wait, Mr. Toller, I have a question.
Go ahead.
Where did you get? Oh, okay, so that's an equal sign? Infinity times ln1 equals?
Yeah, I'm sorry, I didn't.
Okay.
Yeah.
No, I thought it was a minus sign and I was real confused.
Okay.
So thank you.
Yeah. What is, I just looked at the chat. I don't know who DaBaby is. Also, does he wear backwards flex fit hats? All right, here's what I was asking. What is the reciprocal of cotangent? It's tangent, right? So I think it makes sense to rewrite this product as, whoops, I'm going to keep this factor the same, natural log of 1 plus sine 4x. I'm going to divide by 1 over cotangent x, which, as was just pointed out, 1 over cotangent x is just tangent. So this is really natural log of 1 plus sine 4x over tangent x. All right, so now if we try and evaluate our limit by substitution, if I plug that in, so if I do 0 here, I get natural log of 1 over tangent of 0. Natural log of 1 is 0. Tangent of 0 is also 0. And finally, I have this in a form where I can take L'Hopital's rule. All right, so natural log of y. So now I'm going to use L'Hopital's rule. We're going to take the derivative of the numerator and the derivative of the denominator.
Mr. Toller, sorry, I know I'm asking a lot of questions, but what did you just do to get from natural log 1 plus sine 4x over tangent x? And then you did something to
Oh,
get
I'm
the
sorry. Then I
natural
just did, I once again just did my direct substitution. I plugged in 0
Okay.
just to show that now we are in, we're still in an indeterminate form, but now we're in an indeterminate form of type 0 over 0. And that's the type that we can apply L'Hopital's rule to, right? So now I'm ready to take the derivative of the numerator and divide by the derivative of the denominator. And then I'm going to apply my limit again.
So you put in 1 for the x values?
I put in 0 for the x values. We're looking at x as x approaches 0, right?
Mm-hmm. Okay, that makes sense. Thank you.
All right, so the derivative of the numerator, we got to use the chain rule here. So this one's a little bit messier. So chain rule says derivative of the outside function, which is natural log. So it's going to be 1 over 1 plus sine of 4x times derivative of the inside function. Well, the derivative of 1 plus sine of 4x, derivative of 1 is 0. Derivative of sine of 4x is going to be cosine of 4x times 4. All right. Over derivative of the denominator is derivative of tangent, which is secant squared. All right. So if we let x approach 0, of this is kind of a mess, but that's okay. It works out just fine. All right, so if I do a direct substitution now, what we end up with is 4 cosine of 0 over sine of 0 over secant squared of 0. All right, looking back at our unit circle, we know that cosine of 0 is 1 and sine of 0 is 0. Oh no, I'm sorry. This should be 1 plus sine of 0 there. So what I end up with is 4 times 1 over 1 plus 0 over, and secant is just the reciprocal of cosine, so secant of 0 would also be 1. All right, so this whole thing just comes out to 4. And last step here, remember that what we found here was not the actual limit that we're looking for. We found the limit as x approaches 0 of natural log y. And what we really want is the limit as x approaches 0 of y. So we found this. But what we want is just the limit as x approaches 0 of y, because we let y equal our original function, right? We said y equals the 1 plus sine 4x to the cotangent x power. So we need to undo the natural log at the end of all this. And to undo natural log, we're going to exponentiate by base e. Then what we're left with is that the limit as x approaches 0 from the right of y is e to the 4th, and that's our final answer. Final answer is e to the 4th.